Okay, so let's get into some baby chemistry. So in order to understand radioactivity and how understanding that leads us to the age, let's go way back to looking at some very basics. So when we talk about an element, right, an element is a substance that can't be broken down into anything else. For example, right, oxygen is just oxygen, right? I can't break it down into anything else. The smallest unit of measurement is an atom, right? That's one particle. So when we combine particles, that's called a molecule, right? So for example, water's chemical formula is H2O, right? That's a molecule. 2 hydrogens and for every 1 oxygen. Now, if we look inside an atom, there are 3 subatomic particles. We have our protons, our neutrons, and our electrons. What's important here is understanding these 3. Protons have a positive charge. They do have mass, right? So they contribute to the overall weight, but they have a positive charge. A neutron is neutral. It has no charge at all, but it does have weight, right? So it contributes to the overall mass. An electron has a negative charge. Now it does have mass, but it's really, really tiny, so we don't really count it too much. So the important thing here is that if you've ever taken chemistry, you know everything likes to be balanced, right? So if I have a substance that has 8 protons, it's probably going to have 8 electrons and 8 neutrons, right? So everything tends to like to be balanced, which leads us to this great little guy over here. You've probably seen this before, I hope, right? This is the periodic table of elements. And on the periodic table of elements, you'll see 3 things. The first thing you'll notice, right, is the actual element name, right? He stands for helium. Now, you're also going to notice above there is a number and below there is a number. The number above is what we call the atomic number. This is the number of protons in each atom. For example, if we look at gold, gold has 79. So that means there are 79 positives. If there are 79 positives, how many negatives am I going to have? 79, right? Positives and negatives always balance out. Now, the number below is called the atomic mass number. This is the number of protons and neutrons, right? What has the mass? So if we look at oxygen, we see oxygen has, let me get rid of that there, has 8 protons, right? Because I see that number above, so it has 8 positives, which means it has 8 negatives. So if I want to figure out how many neutrons it has, I look at the number below, and I see it's 16. So remember, that's protons plus neutrons. So I got to do some checkbook math here, right? 16 minus 8 equals, right, 8 neutrons. So oxygen is balanced. It has 8 positives, 8 negatives, 8 neutrals. Now, sometimes we have these things called isotopes. An isotope is an element that has different numbers of neutrons, making it lighter or heavier. Obviously, the neutrons do not affect the charge. The charge is the fingerprint, right? 8 means oxygen, right? 27 means cobalt. Okay, 82 means lead. Okay, so those positives and negatives is what gives the element its identity. Okay, those neutrals help give it the weight. Now, one that we're going to talk about quite a bit when we get to chapter 15, 16, and 17 is oxygen. So normal oxygen is oxygen 16, right? As we just saw, 8 positives, 8 negatives, 8 neutrons. However, when we look at the global warming debate, there is an isotope of oxygen. It's called oxygen 18. It has 8 positives, 8 negatives, and 10 neutrons. So it's heavier than normal. Now, because it's not balanced, do you think this oxygen is happy? The answer is no, right? It is not happy. So what this oxygen atom is going to do is it's going to start kicking out particles, these subatomic particles, in order to become balanced. So the different kinds of particles it kicks out there's several. There's alpha, beta, and neutrons. The one we are interested in for geologic purposes is the alpha particles. An alpha particle has a charge of 2 and a mass of 4. So what happens is that oxygen 18 is trying to become balanced, right? It wants to have the same number of protons, neutrons, and electrons. So it kicks out this particle. However, when it kicks out the particle, it weighs less, but it also changes its charge. So I want to go back to the periodic table here. Let's get rid of this. So oxygen, right, if it loses a charge of 2, does it say oxygen? The answer is no. It turns into carbon. Okay. So when it starts kicking out these alpha particles, right, these elements change into something more stable. And it's going to keep kicking out these alpha particles until it's balanced, till maybe it has 6 protons, 6 neutrons, and 6 electrons. It's going to keep doing that. Okay. So this alpha particle is critical here. So this change is what we call the parent and daughter element. The parent is what it starts out as. The daughter is what it turns into. Okay. Now, what's important about this? The most important thing is that those alpha particles are kicked out at a regular rate. Now, it depends on the element. They're not all the same. We can't say all elements kick out an alpha particle every 3 days. It depends, right? Carbon might kick out particles faster than, say, uranium, right? So it all depends on the particle. But what is the most important about this, okay, is that the rate of decay, right, kicking out those alpha particles, is time dependent. It is not mass dependent. So what that means is if I had a teaspoon of uranium and a garbage truck full of uranium, they decay at the same rate because they're kicking out particles, let's say, once every 300 days. Right? It's not mass dependent. That's what allows us to help figure out the age. And I'm going to show you that here in a second. So when it starts kicking out these particles, this leads us to another concept called half-life. Half-life is the time it takes for the amount of the element I have to decay in half. Right? So let me click here to the next one. So if we take a look at this diagram here, okay, and this is a generic diagram and it works for every single element. If I start with 100% of my parent material, let's just use that oxygen 18. I start out with 100%. Okay, meaning, let's say I take my little rock and I look at it under a mass spectrometer and I see I have 10 atoms, right? So that's my 100%. I want to figure out how long does it take to go from 10 particles to having 5 particles. That's half-life, right? Taking that 10 and cutting it in half. So, right, the second half-life would be taking that 5 and cutting it in half, right, having 2.5. So what I can do, right, is I can take a look at my rock, and let's say I pick up a rock, and I notice, all right, that I have, let's use this example here. Let's say potassium-40 has a half-life of 1.3 billion years. That means it takes 1.3 billion years to go from 100% to 50%. And to go from 50% to 25%, right? Each step takes 1.3 billion years. So what that means is if I start with 1 milligram of potassium-40, 1.3 billion years later I have half a milligram. In another 1.3 billion years I have a fourth, because I'm dividing that half into half. Okay? So to determine the age of the rock, all I need to do is take my sample, put it under the mass spectrometer, and figure out those ratios. Right? So potassium-40 turns into argon. That's its stable end member. So if I had, let's say, 2.5 atoms of argon, and I had 7.5 atoms of argon, I'm looking at a ratio. What I see here is that I have 25% potassium and 75% argon. That shows me that my rock has undergone 2 half-lives. Since I know the half-life is 1.3 billion years, All I have to do is add 1.3 billion twice, and I know my rock is 2.6 billion years old. Right? So that makes it nice and easy, right? And like I said, every element, if we go back and look here, has its own half-life. Uranium-238 has a half-life of 4.5 billion years, whereas uranium-235 is much smaller, 713 million years, right? So every element has a different half-life. Now, when we take a look at the rocks that we're going to sample to figure out the age dates, right? Remember, we have three different kinds of rocks. We have sedimentary, igneous, and metamorphic. Well, we can't use sedimentary rocks. Remember, these are rocks that form from the erosion of other rocks. So if I go to the beach and pick up beach sand, every little grain of sand is going to give me a different date. So I cannot use sedimentary rocks. Metamorphic rocks, when they are metamorphosed, when they change, their time clock is restarted. So I can't use metamorphic. However, I can use igneous rocks. Igneous rocks, the second they are formed, they start decaying. So that age is locked in. Very specifically, what we like to look at is bentonite, which is this layer right here, which is weathered volcanic ash. When a volcano erupts, it's a pretty short-lived event. Even if it takes a month, compare that to geologic time, that's a pretty short-lived event. So we like to look for volcanic ash to get some very trustworthy dates. So there are three isotopes that we like to use the most because they're very reliable. The first is uranium lead. This is by far the most used for geology. We like to look for uranium in our rocks, and then we compare that to the lead ratios. The other two that we use, they can be a little iffy, but you have to be confident in your rocks in order to use them. The first is potassium argon, as we talked about before. The problem is argon is a gas, so you have to be very confident that the gas did not escape from your rock, that you actually have all the material. And we have the same problem with rubidium strontium. Okay, so that strontium kind of tends to leak out over time in our rocks. But these are the three isotopes that we use the most. You've probably also heard of carbon dating. Carbon dating is done the same way, the exact same way. It just has a very short half-life. Its half-life is only 5,000 years, so we don't like to use that one for looking far back into time. Now, a great visual way to see this. Remember I told you that alpha particle is going to leave the isotope. Well, that alpha particle is big, right? It's very big. If I had a chunk of uranium sitting on my desk, I could collect the alpha particles with my hand or a piece of paper. Because it's so large, when that alpha particle leaves the crystal, it leaves behind a scar. This is what we call fission track. So here is a crystal of uranium, and you might notice all those little black specks on there. If we zoom in on those black specks, they're actually little tiny holes. Those little tiny holes is where the alpha particle actually escaped. So what I could do in theory, right, is on a really fun Friday night, I could count up all those little holes and essentially do the same thing as half-life, right? Figure out how old that rock is based on how many alpha particles had left the rock. So, how old is the Earth itself? Well, the oldest rock that we have, the oldest thing that we have is a zircon from Australia, which is a type of mineral that is 4.2 billion years old. The oldest rock that we have is 4.04 billion years old from Canada. However, we know that the age of the Earth is older than that. It's 4.6 billion. Because remember I told you the Earth started out as a molten mass. So if the Earth starts out as a liquid, am I ever going to have solid rock from that first day? No. So what we're going to look at is meteorites. Meteorites help us determine the age of the planet. And we're going to come back and see this in Chapter 8. So I'm going to leave you hanging to be sure that you come to class to see why we use meteorites.